Hi, my name is Jake Bert.
And this is David Ichlokmanian. Our senior project is the development of an environmentally friendly manufacturing method for eco-friendly tackle.
Before we begin, here's a brief overview of our presentation. We will go over some background information, our product and process design, some methods for testing and evaluating our prototypes, the results from those tests, our business case, and what should be done in the future.
Lead and soft plastic lures are extremely damaging to wildlife. One survey done in 2014 reported that 17.9% of caught fish contained an ingested soft plastic lure. Also, according to the U.S. Fish and Wildlife Service, 10 to 20 million animals in the U.S. die from lead poisoning each year. Lead especially affects waterfowl as they can ingest lead through the fish they eat and by ingesting it accidentally when collecting rocks for their nests. Lead is extremely dangerous as ingesting one weight or pellet can cause organ failure and brain damage in these animals. Additionally, lead is also not safe for human exposure.
In today's fishing world, there are many cases of fishing tackle being lost to the environment. The tackle on the market is made of non-environmentally safe materials. Our goal is to design an environmentally safe fishing tackle manufacturing process with alternative, environmentally safe materials.
Our objectives for this project are to design an environmentally safe product and process by picking the safest materials for our lures and weights. The main materials that we've encountered in our research are lead, tungsten, and steel. They are all used for very similar purposes, however some are more limited than others.
Due to the toxicity of lead, the high cost of tungsten, and the low density of steel, these materials are unacceptable.
The two main lure materials are PVC-based or silicone-based. Both are very similar in how they perform and how they are produced. These materials are used because they can be easily injection molded into many different shapes and many colors can be added to them. Lastly, the material can mimic live bait when in the water. The reason these materials are subpar is because they do not biodegrade quickly. In fact, some have even proven to grow in size when left in water. Also, they are not safe for animal ingestion. Based off of the research done in our literature review, which we'll go over in a moment, and the currently used materials, these are the options we plan to evaluate.
For our literature review, we searched the Cal Poly databases and found many research studies done that confirmed the damaging effects of lead and the current materials used for the soft plastic lures on people, wildlife, and the environment. We then searched the same databases for any studies done on the subject of lead alternatives to further expand our options. And lastly, we focused on some of the more attractive material options and researched some manufacturing techniques and the alternative materials associated with them.
We will design the weight and lures, our product, the molds to make them, and we will discuss which process we will think will be the best to produce them on a mass scale. We will also discuss the exact scope of our project.
Scope selection. During our research and work, we ran into an issue with our project scope. We found that all sustainable alternatives did not have a high enough density, low enough cost, or low enough energy consumption to replace lead. This is significant in regards to deep sea and ocean fishing, where high density is preferred to allow the lures to sink quickly. Due to this, we found that our original goal of making a universal replacement will not satisfy the customer requirements for deep sea and ocean fishing, as well as the fact that lead has a larger impact on the freshwater environments. To account for these factors, we chose to focus on weights and lures designed for freshwater environments.
The main things we had to consider in designing our weight were the shape and material. We needed to ensure that our design would be attractive to fish, attached to a lure, be moldable, and be environmentally friendly. Here's a chart containing all materials we considered for our weights. This list was developed based off of our research from our literature review and background research. All of the data was obtained from the CES program in the Materials Engineering Department. We only looked at material properties that we thought were relevant to our customer requirements. Once we had all the necessary data, we created a decision matrix to help decide which material is most suitable for our product. All of the properties listed are important, but we applied the heaviest weight to price, density, casting consumptions, ease of manufacturing, and toxicity. To our dismay, our decision matrix found that lead was the best option overall, despite its toxicity to humans and animals. This explains why most companies choose to use lead even though it can harm local wildlife. It is the cheapest, lowest consumption, easily manufacturable heavy metal. We decided to proceed forward with the second best option, brass, as it is non-toxic to wildlife and still has many of the same desirable properties as lead.
We modeled our design off of existing tackle. We wanted to use a fish head shape to help attract fish. It also contains a set of spikes along the shank of the hook to help hold the soft lure in place. Due to the density differences between lead and brass, we needed to adjust the size of our weight to account for the differences in mass. If you look closely, you will notice that the outermost walls of our model have a 5-degree draft to ensure and ease the extraction from the mold. Mold design. For casting our weighted hooks, we decided to use graphite as our mold material. Due largely to its high heat tolerance, machinability, low environmental impact, and because it can be used to produce multiple castings before remachining or replacement is necessary. Unlike investment casting, which is the traditional method of casting brass. During the design of our mold, we had to consider the placement of the hooks, which in our case are the cores, the placement and distances between mold cavities, dowel pin locations, the dimensions of our pouring basin, the combination sprue and riser, runners, and gates, all while keeping within the 5-inch by 4-inch maximum dimensions of the build plate available to our machinists. Taking a closer look at our mold, you can see the cavity above the fish head. This, along with the small channel cut at the end of the mold cavity, were implemented to hold the cores in place. In addition to holding the core in place, the rear channel and clearance cuts double as air evacuation channels to ease the flow and help reduce back pressure in the mold.
Our lures need to succeed at the following criteria, as well as be attractive to fish. Much like weights, we again used a decision matrix to pick the best material. While creating the matrix, we found we had to make far too many assumptions about the strength, flexibility, and dissolution rate of the materials due to the lack of available information. This led us to make a decision that we would have to test all of these practically. We decided not to include bioplastic due to their lack of availability and their need to be injection molded. In order to test our materials, we designed a manufacturing process that we would also be able to use for mass manufacturing if our materials are successful.
The dies for the lures were designed in SolidWorks and 3D printed in PLA plastic. This process allows for design changes to be implemented quickly. We mimicked the design of some of the most common lures sold in the current market.
We used 3D printing to fabricate a pattern board to create the molds that will be used for our lures. These will be used as dies which will be punched into cornstarch. This method of mold creation is the industry standard for making gummy candies. We intend on adapting this method of production for our lures.
As you can see from this clip of Discovery Channel's How It's Made, cornstarch is the standard mold material utilized in the gelatin molding industry for gummy bears and gummy worms. It's low cost, environmentally friendly, reusable, and is a proven manufacturing process. For these reasons, we chose to use this in our process.
Our final SolidWorks design contains 7 worms and 6 fish per plate. The notches in the plate are to allow the operator to easily remove the plate with minimal disturbance of the molds. Ideally, this would be done by a machine. These molds were also designed with 3 degrees of draft to prevent deformities in the cornstarch.
After completing the designs in SolidWorks, the part files were then converted to STL, stereolithography, format, then imported into Cura, where the print settings and G-code were produced. Shown here are the materials we used to make our prototype lures. Testing. To test the viability of our lures, we went to a nearby lake and performed a durability and castability test. During these tests, we tried multiple material combinations of pure agar, pure gelatin, and mixed ratios of the two. In order to test the castability of our lures, we attached them to hooks and cast them out and reeled them in multiple times. This was done to determine their ability to withstand the forces of casting.
As you can see from this chart, the only material that was able to withstand all of our test casts was the store-bought gummies. Anything containing agar failed immediately, and gelatin only survived a few casts.
To test durability, we placed our lures in water and watched over time to observe their dissolution rate.
We were looking for the material to last in water for more than a few hours, but also to dissolve in water in less than 3 days. All of the materials succeeded in this aspect, but were no longer structurally sound after 6 hours in the water.
Customer requirements state that our weights and lures must be effective in catching fish. When we tested this, we were unsuccessful. However, a larger scale test with many more fishermen would yield much more reliable results.
After creating and testing our prototypes, we found that our concept of using gelatin and agar mixes were not successful, but store-bought gummy candies work very well. Acquiring a proper recipe and adjusting to our specifications would show that this concept is still viable.
From a consumption and monetary point of view, we cannot recommend switching to any of the lead alternatives that we listed. However, removing lead from the environment would greatly help all wildlife in areas where lead weights are used.
We were unable to find a monetary benefit for switching away from lead. However, switching to a different material could have large and lasting effects on the local environment. Additionally, we found that switching to a gummy-based alternative could save a company money and help the environment. While completing our project, we had some ideas for future works that others could accomplish. A team could potentially design a process to create coated lead weights, essentially full metal jackets. This could help reach a proper density for ocean fishing. Another project that we had in mind that would be in this field could be to find an environmentally safe alternative for fishing line.
Thank you for your time, and we hope you enjoyed our project presentation.